This is a video on infinite limits of functions. So the first thing we'll start with is what's like our usual setting for this stuff. So we've got some domain A, that's a subset of the real line, and we've got some function whose domain is A. And let's say C is some real number that's a cluster point of that set A. So here's kind of the new concepts from the older videos. So we'll say that this function f tends to positive infinity as x approaches c if the following happens. For every real number alpha, there exists some delta greater than 0 that probably depends on whatever alpha is, such that, again, if x is not equal to c, but x is within delta of c, then f of x should be bigger than alpha. And what we'll write then is the limit as x approaches c of f of x is equal to plus infinity. I think we got a picture for you over here just to make sense of that. So what am I saying? If you had your function y equals f of x here, then for any alpha that I put down, what I'm trying to say is I should be able to find some window around c so that for any x value that I was to pick inside of that window, say that's my x, when I plug it into my function, its output, this thing right here, that y value, is higher than that alpha. So for any one of these alphas on the y-axis, right, I should always be able to find some window around c so that the outputs of all the outputs of my function are above that particular alpha. Okay, cool. And so there's one more of these that I think I want to tell you about, which is, we'll say that f tends to negative infinity as x approaches c if, and it's a similar definition where for all real numbers beta now, there exists some delta, so delta probably depends on what beta is, such that, again, same idea, I don't want x to actually be equal to c, but I do want x to be within delta of c. I should have then that f of x is less than that beta. And we'll write then that the limit as x approaches c of f of x is equal to negative infinity. I think I've got a picture for you over here as well. So what am I trying to say to you in my picture here? I've got this green function, which is f now, and I care about what's going on around c. My x values are near c. So if you were to throw any beta on the y-axis, so I just randomly picked one there, then what should I be able to do? I should be able to find some window around c so that, again, for any point that I picked inside of this window now, say this one here, oh, that's not a highlighter though, for this one here, if that's x, when I plug it into my function, it's right there, and the point is that its y value is below that beta. So for all the y values in this window, they are below that beta. So for any beta, you should be able to find a window so that all the y values in that window are below that beta. Cool. So let's do some Excel examples to maybe get used to how do we use these definitions. So to show that the limit as x approaches 0 of 1 over x squared is positive infinity, given some alpha, by the way, that's greater than 0 here, instead of just alpha and r, why am I saying that? Just because I know 1 over x squared is always a positive number. So I can just get away with, instead of up here for all alpha and r, for this particular function, just positive alphas suffice. But what do we want though? I want to find some delta that's positive so that if x is within delta of 0, right, 0 is like my c, then I want 1 over x squared, my function, to be larger than alpha. And so what we'll do is, it's kind of like the epsilon proofs we're maybe used to at this point. We'll start here and we'll try to work backwards to get some relationship between delta and alpha. And so maybe what you see is that's equivalent to saying that x squared is less than 1 over alpha, right? Since they both have the same sign, I can just take the reciprocal and the inequality just flips around. And then I'll just solve it for x. So that's true if and only if x is less than 1 over the square root of alpha. And so, well, here I want x to be less than delta, right? Since x is positive, since I'm, or I guess I don't know x is positive, absolute value of x is positive. So what should I do in that case then? I should just let this be my delta here, and then I'll win the game. So we'll let delta be 1 over the square root of alpha. And so let's look at like what would the formal proof be. Remember, that was just the scratch work there. Just to remind you that for a lot of these types of proofs, you kind of work backwards, and then your actual formal argument is going to run this way. So start with some alpha that's bigger than 0. And again, we just kind of jump straight to the punchline, right? That delta should be 1 over square root of alpha. Then what happens? Well, if x is within 1 over square root of alpha of 0, then, again, if I was to square both sides, that tells me that x squared is going to be less than 1 over alpha if I square both sides of this. And I don't need the absolute value on the left anymore. And that's true if and only if, when I take reciprocals now, again, these have the same sign. So when you take the reciprocal, this inequality should flip around, and I achieve that 1 over x squared is larger than alpha. So what else do I want to do in this video? Just extend this idea of an infinite limit to one-sided limits as well. Oh, I'm not there yet. I jumped the gun. That's coming soon. So there's some kind of comparison, kind of a comparison theorem for these infinite limits too. So let's suppose I had two functions now. So I probably should have told you that g also goes from a to r as well. But let's suppose that g is always taller than f for all x in my domain. And then what do I want to say? Well, if the limit of f of x is positive infinity, then the limit of g of x is positive infinity as well, right? So if the smaller one goes to infinity, then the bigger one does too. And I've got a picture for you down here. If I know that the green function has to go to infinity, right? That means that for any alpha, there should be some window around c so that all the outputs within that window are above that alpha. Well, then the same is true for any function that's larger than f also. Any function that's always larger than f. And so in particular, that same delta that worked for f, it's going to work for g too. And you'll see that in the proof in a minute. But what's the other part of this kind of comparison theorem? Part 2, if the limit of g of x is equal to negative infinity, well, so in other words, if the bigger function goes to negative infinity, well, then the smaller one has to also. And so if I give you a picture of that, if I started with the blue there, right? I've got the blue function, and I know that it goes to negative infinity. So remember that for any beta that I picked, there should be some window around c, so that for all the x values in that window there, maybe you can't see it very well, but all the blue y values, right, are below that beta. Well, if all the blue y values are below that beta for this particular delta, then all the green y values are also below that beta for that particular delta. And again, you'll see that in the proof in a minute. So what's the proof look like? I think I just proved one because the other proof's pretty similar. So what if we suppose that this happens? And what I want to conclude is that the limit of g of x is also positive infinity. Well, let's let alpha be some positive number in this case. Then so by hypothesis here, right? Since this happens, I know that there exists a delta so that if x is within c of delta, well then f of x is larger than alpha. So now let's compare f of x to g, right? I want to say something about then g of x does some cool stuff. And so here's where I'm going to use the fact that, oh, I know that g of x is always larger than or equal to f of x. And so what I'm going to do is g of x can just go on this side of that inequality. And so in particular, by hypothesis, f of x is less than or equal to g of x. Therefore, g of x is also larger than that alpha, again, whenever your x's are within that delta of c. And hence, so what does that mean then? You just showed that the limit as x approaches c of g of x is positive infinity as well. And the proof of part 2 is a pretty similar argument. All right, so now you can have infinite one-sided limits as well. And so same setup, a is some subset of the real line, f is a function whose domain is a, c is a cluster point now of a intersect the interval from c to infinity. All we're trying to say is that I'm only looking at stuff in a that's to the right of c. Then, here's a few things. The limit as x approaches c from the right of your function is positive infinity, if and only if, and this should look all pretty similar. All that's different here, if x is approaching c from the right, well then x is bigger than c. So therefore, I just need to consider x minus c here less than delta, right? I already know x is larger than c, therefore x minus c is positive. But you notice it's the exact same idea of an infinite, but the limit going to negative, oh, sorry, that's a positive infinity, right? It's a plus sign. But limit going to positive infinity, the rest of this looks pretty symmetric to what we wrote above. And I got a picture for you here. Ta-da. So here's my function, and all I care about is to the right there, can I put some window around c so that for all the x values in this window, when I plug that into my function, it spits out a y value that's above alpha. If for any alpha you can put such a window around c, then that means that your limit goes to infinity from the right. Part 2, we'll say that the limit from the right, again, so from the right, is negative infinity if and only if, and it's the same definition as above. Again, the only thing that's different than what we started with is that I don't need the absolute values here because I know here, since x is coming from the right, that x is already larger than c. I think I've got a picture for you over here. So again, for any beta that you were to put on the y-axis there, right? I know that there should be some window around c so that for any x value I pick in that window, when I look at the y value, it's below beta. So that means that f goes to negative infinity in that case from the right. And there's a corresponding definition to say that for the left-hand limits. And so what's different now? This is trying to say that I'm looking at points in A that are to the left of C. Then what we'll say is you go to positive infinity from the left if, same idea, and again, if you're coming from the left, then that means that c is to the right of x, so therefore c minus x is positive now. And so that's really all that's different in this definition. I've got a picture for you over here. Same idea, for any alpha you were to throw down here, you should be able to find some window around c, so that if I take an x value in that window, any x value in that window, and I look at its corresponding y value, again, it's above alpha. And depending on what alpha is, maybe you need to get closer to c. But the point is that you always could, so that the outputs are above alpha. And similarly, we'll say that the limit from the left is negative infinity if and only if, again, you can get close enough to c so that your outputs are below any beta that you were to give me. And so to give you a picture of that, if I was to, here's my function, which is green here. I'm saying if you were to put any beta on the y-axis, right, I can find some window around c, which in my case is just this one right here, so that if I was to pick any point in that window and look at its corresponding output, again, it's below beta. All right, so let's do a concrete example. I want to show the limit of 1 over x is positive infinity when I come from the right. And so just to show you kind of some scratch work, how would you get started? Given some positive number alpha here, just because I know I'm coming from the right, I only need to look at alphas that are positive, and I'm going to positive infinity. What do I want? I want a positive delta such that if, again, coming from the right, so I don't need absolute values in the middle there. If x is less than delta, basically, then 1 over x should be less than alpha. I'm going to start here to try to get a relationship between x, alpha, and delta. And so in that case, that says x should be less than 1 over alpha. So wait a minute. If x is less than 1 over alpha, that's the same thing as saying 1 over x is bigger than alpha. So why don't I just let this delta be 1 over alpha? Cool, and that's the trick. So what's the formal proof look like? For any positive number alpha, choose delta equal to 1 over alpha. Well, if x is within delta of 0 then, remember 0 is your c here, this c right there, then what happens? 1 over x, well that's bigger than 1 over delta, right? If you take reciprocals of this, since they have the same sign, I just flip the inequality around. But then 1 over delta, that's this thing here. I probably should put that's equal to alpha, so that is not true what I've told you there, equals alpha. But the point, 1 over x is bigger than alpha. So we should be pretty happy about that. I think I've got one more example for you. So the limit of 1 over x when you come from the left now towards 0 is negative infinity. So what do we want to show? Given any beta that's in R, and really I can get away with beta that's less than 0 since I'm only looking at these that are negative here, I want to find some positive number delta so that whenever, remember, now x is to the left of 0, right? So 0 minus x is positive. So whenever 0, again, is and x are within delta of each other, then 1 over x should be less than beta. Same idea. We're going to start there. Try to get a relationship between beta and delta. So that says that x is bigger than 1 over beta. But that tells me that negative x, which remember, if I'm coming from the left, x is negative. Therefore, negative x is positive. That's crazy, but I'm just saying that to you right here. But then that's going to be less than 1 over beta here. And so now, by the way, if I make that correction that beta was less than 0, well then 1 minus 1 over beta is a positive number also. Okay. And so I should just let the delta be this number minus 1 over beta. So that's my scratch work there to come up with the delta. So what's the actual proof look like? Start with the beta that's negative. So if, again, 0 minus x is less than minus 1 over beta, and remember, these are positive numbers in this case, then what happens? What do I get? Well, if I was to take the reciprocal of both of these, again, since they have the same sign, I just need to flip the inequality here. So minus 1 over x is bigger than minus beta. But then I'll multiply both sides through by that negative, and I get that 1 over x is less than beta, which is exactly what I wanted to have happen.